Welcome back again. This is going to be part number 8 of virtual topologies in MPI and episode number 36 in learning by doing MPI. So we're going to continue from where we left off last time. So Final Cut is also running in the background, rendering that previous episode. We have seen the first example of MPI neighbor all gather V, and now we want to see the second example, which is MPI neighbor all gather V, V1, the first version. Let's see the difference. MPI neighbor all gather V, V1. So these things are the same. You can see that we're using, again, 8 processes here. And we have a ring topology. Again, the same mechanics also goes here. And then we are using the distributed graph adjacent constructor. And then you see that the difference is that this time, this is a slightly more complex example. Here we are using a variably sized send buffer. We are using the rank of every process to determine that. The reason that we put rank +1 here is because for the root process, it's going to be 0 + 1, it's going to be 1. If I put only rank here, it's going to be problematic because the send buffer is going to be 0. And then every process basically is going to fill that send buffer with the rank of itself. And the receive counts is again a variable receive count size. And the reason for that is for the root process, for example, is source 0. That's the process before. It's going to be 7 + 1 is going to be 8. So we are receiving 8 counts from process 7 or the neighbor before root process. And the second element is sources 1, which is actually the proc after. And that is process 1. 1 + 1 is going to be 2. So we're going to receive 8 integer values from process 7 and 2 integer values from process 1. This is the case for root process. For every other process, it's going to be different. Displacements, it has 2 elements in an array, and then the first one is going to be 0. The second one is going to be receive count 0. That is the first amount of elements that you received. That's going to be that much difference. And you see that displacements in this case, it's not in bytes, but it's actually in the number of data with that specific type, which in this case is MPI int or integers. Receive buffer, again, it's a variably sized receive buffer. You can see that it's a source, it's the summation of all the data that processes before and after are going to send to the current process. In the case of root process, it's going to be 7 + 1, it's going to be 8 elements from process before, and it's going to be 1 + 1, which is 2. It's going to be the number of items that it's going to receive. So receive buffer for root process is going to be 8 + 2, which is going to be 10. We're going to check that in a second. Then we are using this MPI neighbor all gather V. We pass in all the corresponding and correct sort of arguments. And then you see that we have a print statement here, which is sort of variable because it depends on the receive count. And receive count is not actually the same for all the processes, right? So let's run this example, MPI-CC, MPI neighbor all gather V version 1. And I'm going to run this with 8 processes. You see that process 0, this is what I said. We have 8 7s from the process before, that is process 7, and we have 2 1s, which is basically from process after. So that's the basically logic. And you see that the amount of data being sent and received are not basically the same. The least amount of data transfer happens for process 1 because process 0 only sends 1 0. That was rank +1, the send buffer, you remember. And it gets also 3 2s from process 2. And the maximum amount of data transfer happens for the process 6 because it gets 6 5s from process 5, and it gets 8 7s from process 7. Okay, so now we move on to, again, we have seen this one that the in-place option is not meaningful for this operation. As I said, again, if you don't know what in-place is, please go back and watch the collective communications in MPI episode. It's just a series of episodes as well. The next one on the line is neighborhood all-to-all. In the neighborhood all-to-all operation, each MPI process I receives data items from each MPI process J. If an edge of J and I exists, again, J sends and I receives. Similarly, each MPI process I sends data items to all MPI processes J where an edge between I and J exists. This time, I sends and J receives. So this code is more general than MPI neighbor all gather. So what is the difference of MPI all gather and all to all? The difference is that MPI neighbor all to all is more general compared to MPI neighbor all gather in the sense that different data items can be sent to each neighbor. So we're going to see that in a second. The kth block in the send buffer is going to be sent to kth neighboring MPI process, and the lth block in the receive buffer is going to be received from the lth neighbor. So the second part of the sentence also is valid for all gather operation, but the first part of this is exclusively valid for all-to-all neighborhood collective communications. So here you see that the first one on the line is MPI neighbor all-to-all. Let's see what kind of data it gets. We don't see any difference. It's the send buffer, send count, send type, receive buffer, receive count, receive type, and the communicator. And then you see that all of these are inputs other than the receive buffer, which is going to be the output. And you see that this procedure also is valid for Cartesian communicators, for graph communicators, and for distributed graph communicators. And then again, if the communicator is a distributed graph communicator, then the outcome is going to be as if that each MPI process sends to each of its outgoing neighbors and receives from each of its incoming neighbors. And there's a portion of code here to basically, as a template, shows you how this thing looks like. And then we have the type signature, similar to before. We have the type signature, so the amount of data pairwise between every MPI process should be the same. And again, the in place option is not meaningful in that case, and all arguments are significant on all MPI processes, and the or the communicator must be the same for all of those MPI processes. And then we have one example here which we don't care about, but there is a figure 8.3 right here, which basically shows a Cartesian scenario where we have on the right hand side you see that we have one process in one dimension, and on the left hand side we have three processes in one dimension. So this is how it looks like if you want to have a better understanding of that. Now we can go back and see MPI neighbor all to all. This is the first version or the first example. All to all.c. Again, this thing is the same. We're using 8 processes. We have the ring topology. The same mechanics goes here as well. We're using this distributed graph adjacent, but the difference is right here. If you remember, in all gather, we had only the send buffer, the rank of every process. But in this case, we have an array with 2 distinct values. One is the rank, and the second one is the rank squared. So we are sending different items or different data to each neighboring process. And then the receive buffer is going to be the same size of 2, because again, in a ring topology, we are sending one integer to the process before, one integer to the process after, but these integers are different. In the case of all gather, these integers are the same. In the case of all to all, these integers are different. In this case, to one process we are sending rank, and to another process we are sending rank squared. So here we are using MPI neighbor all to all. We pass in all those proper arguments. Send buffer, the counts, one integer, again, as I said, in a ring topology, and then the receive buffer, one integer, yeah. And then every process basically prints its information. So let's just run this. And how many processes? 8 processes is okay. And then you see that from process 0, we have 49 and 1. For process 1, we get 0 and 2, and so on and so forth. But you might be wondering that here we said send buffer is rank and then rank squared. But in the receive buffer, you see that process 0 got 7 squared and 1. So we got rank squared and then we got ranked. So what's going on here? it's very simple. If you put it on a piece of paper, you're going to understand it very simply, but I'm going to try my best to describe it right now. Process 0 is going to receive items. One from the previous process, which is process 7, and one from process after itself, which is process 1. So now let's take a look at the perspective of the previous process, which is process 7. Process 7 has a send buffer. The send buffer is going to contain 7 and 49 in itself. Now remember this statement here. The kth block in the send buffer is going to be sent to the kth neighboring MPI process. So the 0th element of send buffer of process 7 is going to be the first neighbor of process 7, which is process 6. So you remember we say before and then we send it to after. So before, after. So what is before process 7 is process 6. So that is why process 6 gets 7. But what is going to be sent to process after process 7, which is process 0? It's rank squared. So that is why we get 49. So in send buffer, we have rank and then rank squared. But in receive buffer, we always get rank squared and then rank. So you see the difference. I hope you understand this. If not, then put it on a piece of paper, put these processes consecutive, process 7, process 0, process 1, and then try to write down the send buffer for every process, and then try to imagine that what's going to be basically the receive buffer for process 0, which is in between. So yeah, we can move on to the next example. I actually wrote in my notes here, I have written here for MPI neighbor all to all.c, compare process 7 with figure 8.3. So this is what happens in process 7. We have 36 and 0 with this figure 8.3 right here. I put here 7, and you kind of see that the first element in the receive buffer of process 7 is going to be the second element of the send buffer of process 6. And the first element and the second element in the receive buffer of process 7 is going to be the first element in the send buffer of process 7. So maybe it was better to put process 0 here. So I should maybe do this. Put process 0 here. This is going to be process before. So I'm going to delete that. And process after this is going to be process 1. So now you see that from process 0, the second element in the send buffer is going to be the first element in the receive buffer of process 0. And that is what is happening here. This is what I was trying to say. The second element in the send buffer of process 7 is going to be 49. Is going to be the first element in the receive buffer of process 0. That is what is happening here with this arrow here. And then the second element in the receive buffer of process 0, which is this one, is going to be the first element in the send buffer of process 1, which is going to be rank and rank squared. So the first element is going to be rank. In the case of process 1, it doesn't matter because rank and rank squared, both of them are going to be 1, but this is exactly rank. I'm going to tell you to make sure that this is rank. This is not rank squared. So now you kind of understand with this visual. So between 7, 6, and 0 was not a proper way of doing it. So this is maybe the proper way of doing it. So with process 7, with process root or 0 in between, and then we have processes 7 and 1. And we saw this beautifully with this graphics. Okay, now we can move on to the next example, which was MPI neighbor all to all, V1, the version 1. These things you see all the same. We have 12 processes. We have a Cartesian grid, 3-dimensional. Again, we have the same molecule, which in ideal case, it has 6 neighbors. That is why we have receive buffer with the size of 6. We initialize it with all -1s. And then the send buffer, in this case, it's not only the rank, but it's an array with 6 values. And you see that we have alternatively rank, rank squared, rank, rank squared, and rank squared. So the same drill happens here, but in the communication, only these two changes, and then we are using MPI neighbor all to all. And then every process basically prints its own information. So I'm going to quit that MPI CC, MPI neighbor all to all v1.c, and we run it with not 8 processes, but 12. And for example, for process 0, we get these sequence of data. And if you remember in all gather, you remember we got 8 and then 4 and then 2 and then 2 and then 1 and 1. So now we get rank squared, 64. That was process 8. And then we get rank. We get rank squared. We get rank. We get rank squared. We get ranked. So 2 squared is going to be 2. 1 squared is going to be 1. 8 squared is going to be 64. And the reason, so again, the same scenario goes here as well. We started with rank and then rank squared. But you see that for 0, we get rank squared and then we get rank. Again, you need to go back to the perspective of the process before this process, which is process before this process in the 0th dimension is going to be process 8 because it's going to be -1. We don't have -1, so we have periodic conditions. It should be 2, 0, and 0. 2, 0, and 0 corresponds to process 8. From the perspective of process 8, the send buffer sends first rank to the process before process 8. What is process before process 8? That is 2, 0, 0. It's going to be 1, 0, and 0. 1, 0, and 0. So 1, the first neighbor of process 8 in the 0th dimension is process 4. The second neighbor, that means process 8 is going to send 8 to process 4. So if you take a look at here, you see that there is 8 here. Now you understand what I mean by that, right? So from perspective of process 8, rank is going to be sent to process before, to the first neighbor of process 8 in 0th dimension. And the second neighbor of process 8 in 0th dimension, take a look at it. So it should be 3, 0, and 0, but since we don't have 3, but we have periodic conditions. So this means that it's going to reset to 0, 0, 0, 0. So the second neighbor of process 8, which takes the value of rank times rank or rank squared, is going to be process 0 or the root process. That is exactly why we get 64, 4, 4, 2, 1, and 1. I hope you understand it well with this example. So the first example, again, was a distributed graph. The second example was a Cartesian grid. And the last example, MPI neighbor all to all and V2. This is, again, the same drill as example 8.2 with a pattern of 1, 3, 0, 3, and 0 and 2 right here. And we use a distributed graph, not the adjacent one, the most general case. We're using this inquiry function. So far, we have seen all these code examples in previous topology constructors already. And then the magic happens from the neighborhood collective communication, which the send buffer is, again, a rank and rank squared. The receive buffer is -1 and -1. And we can basically run this one as well. Nothing crazy here. Oh, not 12 processes, but 4 processes. There we go. Now, again, you see that we have -1 and -1 here. We already talked about this for all gather case. So you can also use basically in degree to not basically see these minus ones. So I can do the same, but it's exactly the same as before. So if you don't want to basically see this minus one, you could do, what am I doing? Okay. You could do basically a variable sizing here. Instead of having received buffer of size 2, you could use in degree here. And then instead of having a simple print statement here, you can put a for loop here to go through with the number of in degrees, based on the number of in degrees. And then, yeah. And then the same story that why do we get, for example, 9 here, which is 3 squared, is similar to what we were talking about in old examples. I'm not going to stress on that fact again. Okay, so now we can move on. The next one on the line is MPI neighbor all to all V, which is the vector version of this one. It basically gives you flexibility with, with this displacements for send buffer. You see that this is an integer array. The size of this integer array is equal to the out degree, the length of out degree, of course. And then the send counts is again as a non-negative integer array, and then it again has the same length as the value of out degree. Why? Because this is what we basically are going to send, right? And then for receive counts, you're going to end up with having receive displacements or R displacements right here. This is going to be an integer array, and the size of this one is going to be length of in degree. Yeah. So the length of R displacements or receive displacement are going to be the value of in degree. And for the receive counts, again, you have an array here. So take a look at here. So send counts is going to be an array. Send displacements is going to be an array. Then you have your type, and your type is basically not an array. It's just a type. And then your receive buffer, receive counts is going to be an array, and receive displacements is going to be also an array. So this procedure also works with Cartesian communicators, graph communicators, and distributed graph communicators. Again, if the communicator is a distributed graph communicator, then it is as if, you know, the same drill and the same story, and then you have a template code which basically shows that, and then the same drill, everything pairwise should be okay, you know. And then in place option is not meaningful for this one as well. And then all arguments are significant for all MPI processes, and then the communicator must be the same, identical for all MPI processes. And the last one, which with the W, is basically gives you the full kind of flexibility, which send types can be also an array. So if you take a look at MPI send types, this is also an array. But we're going a little bit ahead of ourselves. First, we need to take a look at the examples here. I made a mistake. I haven't put the examples here. MPI neighbor all to all V. So I need to write here C MPI neighbor all to all V dot C and MPI neighbor all to all v1.c. Sorry for the inconvenience, but I forgot to add this here. Whoops. So our time is almost over, 24 minutes or 25 minute-ish. We can take a look at maybe the first example and then finish this episode. Quickly, this is again 8 processes, and we have the ring topology, same mechanics as before, process after. And then here's the difference. We have neighborhood collective communication. We are sending the send buffer in this case is rank squared. And then we have send displacements is the size of 2 because we have 2 in degree. right here, you can see that, sorry, 2 out degree, it's not in degree. And then we have send counts as being 2, receive buffer again is initialized to be -1 and -1, and displacements for receive. And in a loop, we put all those things there. For displacements, we put based on, 0, 1, because we are sending one item we are sending one item to each neighboring process that we have, process before, process after in a ring topology. And then receive counts is going to be 1 because we are always sending only one element to every process. Then here we are using the all-to-all V, the vector variation. We are sending sort of all those proper arguments that we have here. And then every process is going to print its own information. So let's go with MPI CC, MPI neighbor, all-to-all V.c. And we run it, not with 4 processes, of course, with 8 processes. And now you see that process 0 again gets 49 and 1. And the reason why it gets 49, we already talked about it. So I'm not going to show example V1. We're going to continue in the next episode.